Hello, everyone. Thank you for the introduction. So I'm Mustafa, a software engineer at Red Hat that's been working with IBM Research. And today we want to show you how we have come together to simplify distributed training and fine-tuning of large language models and foundation models on Kubernetes and OpenShift clusters using CodeFlare as well as Kubre. So this presentation is going to mainly focus on a demo, but before all of that, I'll give you a brief introduction to what CodeFlare is before showing you how you can get started using it today. So starting at the beginning, foundation models and large language models. I'm sure this is a term you guys have heard maybe hundreds or thousands of times over the last 2 days, but it's kind of why we're all here, right? To be able to train and fine-tune foundation models is something we all want to be able to do on our Kubernetes or OpenShift environments, but it obviously comes with a lot of difficulties and challenges. So if you want to learn all about the challenges that we've faced at IBM and Red Hat on doing that fine-tuning and training in Kubernetes and OpenShift, feel free to check out our talk at 1 p.m. in the Golden Gate C1 to learn about all the details and how we came up with the benefits that CodeFlare brings today. But what I want to do right now is just talk about briefly what CodeFlare is, how it works with Kubre, and how you can get started spinning up array clusters and using them in your Kubernetes environment, both for data scientists and administrators. So what is CodeFlare? CodeFlare is an upstream open source community project that has been built through a collaboration between IBM Research and Red Hat. And it enables batch computing and all sorts of distributed training and fine-tuning on Kubernetes and OpenShift. It's available for everyone today. Images are open, the code is open, you can install it through Community Operator, you can pip install components. Anything you need, we've got for you. So there are 3 main components to the CodeFlare stack you'll need to know about. The first is going to be the most exciting for data scientists and developers. It's the CodeFlare-SDK. This is a Pythonic interface through which anyone from either their local machine or any environment they're working in can spin up an array cluster on Kubernetes, manage it, see status, details, submit jobs to it, develop interactively, and take it all down. All of this can be done straight through Python. The package for the CodeFlare SDK can be pip installed. We also provide Jupyter Notebook images for people who want to try it out. Anything you need to get started so your data scientist has instant access to resources. The next piece is MCAD, or the Multi-Cluster App Dispatcher. This is the queuing system that the array cluster requests actually get sent to before being dispatched to the Kubre operator. So this enables us to do gang scheduling on aggregated resources, and it also allows for a lot of important enterprise features like hierarchical quota management for your organizations, priority, preemption, and all those robust features you need for getting those array clusters and resources to your data scientists. The last piece is InstaScale, and this is an optional piece for on-demand hardware scaling. If you need to spin up GPU nodes fast on your Kubernetes or OpenShift cluster on demand dynamically based on the requests of your data scientists, InstaScale will handle that for you. And once again, all of this is available today. You can install the CodeFlare operator through the Community Operator Hub. Everything's available on GitHub, and we're more than happy to help you get started with this. But looking real quick, you can see kind of what the user workflow that I'm about to demonstrate will look like. An SDK user can submit a request for their array cluster. It'll be passed on to MCAD, and when MCAD says, all right, we've got enough allocated resources on your Kubernetes cluster, and you also have the quota available, it'll then pass that array cluster request on to Kubre, which will spin up the cluster, and the user will then be able to interact with. So CodeFlare and Kubre is not just a one consuming the other situation. We've actually got, between IBM, Red Hat, and Anyscale, direct collaborations on building the future of Kubre that we're very excited about. So the first thing we're working on is the Kubre API server, which will enable all sorts of direct interfaces to Kubre and for developers to get involved with Kubre more easily. We're also helping with testing and security. as well as making sure the CodeFlare-SDK works as a fully supported Pythonic interface to Kubernetes. So, without further ado, let's look at what the stack actually looks like from a user's perspective. So the first thing I want to show you guys, just to get started, is how you can spin up, look at the details and status, and manage array cluster using the CodeFlare SDK. So it's a super straightforward process. All you have to do to get started, if you've pip installed the CodeFlare SDK or you're using a notebook, you can just import the pieces from the CodeFlare SDK that you need. Underneath that, if you want to do any additional authentication, the SDK will by default use default kube configs or default auth. If not, you can use token server auth or pass in your own kube config or in-cluster config, whatever works. And here you can see how we define array cluster. When a user wants to create array cluster, all they have to do is create this cluster object by passing in a cluster configuration and then putting in the resource requests that they need in that array cluster. So they can add the name of the array cluster, the namespace they want it to come up in, and then the workers, CPU, GPU, memory, etc. And once you've got that all said and done, what that generates in the background is an app wrapper YAML getting sent to our MCAD queue that then eventually gets dispatched to Kubernetes once the resources are available for the data scientist. So when a data scientist wants that to come up, they'll call cluster.up. And what that'll do is it'll submit the array cluster request to the system. Now they can check on the status, and if they want to spin until the cluster is ready for use, you can just call a cluster.waitReady. And when your cluster is ready and available, it'll stop spinning, it'll say your requested cluster is up and running. If we look at the status again, you'll see that right here, our array cluster is now up as we expect. You can also see the details of the array cluster to get more information that you might need. You can see that the number of workers, the number of CPUs, GPUs, memory are as we requested, and that all of those details look right. You can also get the cluster URI and more. Now, if you want to use instascale, it's as simple as saying instascale equals true, and when resources aren't available, we will dynamically scale up based on quota the GPU nodes you need. And if there are specific machine types from a cloud that you're interested in, you can specify those directly in the Python here. Now, once again, the rest of that process will look very similar. You can call cluster.up, cluster.waitReady, and it'll all be the exact same as what you're expecting. The waitReady here might take a little longer this time if you're scaling up hardware resources. Before it took a few seconds. Here we used a little magic. It'd actually take 4 to 5 minutes to get those nodes on your cloud provider or on-prem up and running. But you can see here we've got our GPU resource that we needed to scale up, and our cluster is adapted to the data scientist's needs. Now, if we look just ahead here, you can also see within our OpenShift or Kubernetes cluster, you can see the nodes that have actually been added. And if I move over here to the actual metrics page, you'll see we had 0 GPU nodes in the cluster, and when that request came in, we scaled up to 2 GPU nodes. So there's nothing funky going on here. We didn't start with those GPUs. We brought them up exactly when they were needed. So now, how do you use the array cluster that you've spun up? Well, there's 2 ways to work with it, either interactively or via direct job submission. So let's start with the interactive approach. As you can see here, through the SDK, you can also get your array cluster dashboard URI as well as the regular service URI to begin working with. Now the dashboard, as you all already know, is a powerful tool to see a lot of the information you need about your array cluster. You can see the cluster's details, you can see logs per worker node on the head node, and you can also see your job submissions. So here's an old MNIST job that I had submitted earlier to test on. I can see all of the logs of my training here. Everything looks good. If I need to interact with it further, download my logs, check out more details, I can do that here through the Ray dashboard. Or you can get all of these details back on the SDK as well through your notebook directly, which I'll show you in just a second. So you can also get that cluster URI, and that can be used to directly connect to your Ray cluster to develop interactively. So I'm sure you're all familiar with ray.init, passing in your runtime environment, things that you need, your packages you need, and then connecting to your Ray cluster. So that'll look just the same here. You can connect to that Ray cluster you've spun up on your Kubernetes or OpenShift cluster, and then you can submit all of your remote functions, ray.remote, however you need. In this example here, I'm actually doing a Distilbert fine-tuning on the IMDb dataset, just to show that you can handle any of that medium to large sized fine-tuning or training that you might need. Now, this isn't the most interesting example we'll have. In just a couple of minutes, you'll see we also do a GPT-2 fine-tuning on the Wikitext dataset via direct job submission. So that'll come up in a second. But for now, just to demonstrate that the interactive pattern is working as expected, you can see here we've now got that function. We can run our function remotely on the Ray cluster, call array.get to get that information back on what's running, and the logs will begin appearing here. If we look back in our cluster now, you'll see those GPUs that we've spun up are now being utilized to the max. So our GPU utilization has gone from 0 before on those newly spun up GPUs to now being properly utilized for the interactive submission that we've just made to our Ray cluster. So now if we give that just a couple seconds or so, we'll fast forward a little bit and you can see that our interactive function has completed. You'll see it took about 740 seconds to get that fine-tuning done. And from there, the flow is as you'd expect. If you're going to keep doing ray.remote functions, developing interactively, you can. If you wanted to tweak this function, you could do that directly here and submit it again. If you wanted to change hyperparameters, if you wanted to visualize results or data, if you wanted to then do some testing or evaluation, you could add another function. Everything will work just as you're used to with regular Ray, now enabled on Kubernetes and OpenShift in a seamless manner for your data scientists. So now for the final part, direct job submission and that nice LLM GPT fine-tuning example. So as you'll see here, we're going to go through a similar flow. The user is just going to bring up the Ray cluster, request it with GPU resources. We're going to scale that up for the user. They're going to get their Ray cluster back with all those details. And now where the flow changes here is once that Ray cluster is up and running, we'll be doing a direct batch job submission, fire and forget, using an existing distributed training script that we've brought, and just sending that to our Ray cluster to run till completion. So if we can move ahead here. This is just highlighting that there weren't enough resources, and then by bringing down the old cluster, I now have resources to bring up the new cluster, and that it'll dynamically provision everything we need. But scrolling down here is where things get interesting. So what we can do directly through the SDK is submit those distributed training and fine-tuning jobs via TorchX and Ray jobs. So as you can see here, this is a Hugging Face script taken directly from their repo for fine-tuning GPT-2. No modifications necessary, nothing funky going on in the background. This is just a direct GPT-2 fine-tuning script using the transformers library. All we have to do is pass in the name of the job we want to run, the script we want to run, any additional Python requirements we might have, and then any additional script arguments we might have. We put that in a DDP job definition, call a job.submit, and now you're off and running on the Ray cluster that your data scientist has spun up. We've got that GPT-2 fine-tuning job running as expected. So it'll say pending here. If we give it just a second or two, it'll switch to running once the Ray cluster has processed the job request, installed dependencies, and got it up and running. And so now you can see we can retrieve the job status directly from our SDK. You can also get the job logs directly from the SDK as well. And as you can see here, once again, the resources that we requested were fully utilized. This is a fast forward to see the entire training run, how long it took, and the fact that our GPUs were utilized throughout the training run. And by the end of it, our data scientist had a completed GPT-2 fine-tuning job on Ray clusters in a Kubernetes environment that they could launch on their local laptop or machine in just Python. And everything worked for them perfectly. So through CodeFlare and Kubre, we give you the power to do all of that on Kubernetes with ease, open and available today. If you have any more questions, feel free to swing by the IBM Red Hat booth. I can walk anyone through with more detail on the stack, provide links to anything you might need. You can also scan there to see our GitHub. That's all the time I have. Thank you all so much.